Hello, my name is Kantana from Vao-Soongnern University of Technology. Today I will present my research about molecular simulation to investigate structure and dynamics of diblock copolymer thin film. In this work, I am interested in studying new potential properties of polymeric material developed from the existing monomer using the concept of creating the diblock copolymer. For example, in our research group at HUT, we used to design a new bioplastic material by molecular simulation to guide the synthesis of the diblock copolymer between PLA and PET for application as the better partitioner for PLA bioplastic. As we know, for bulk system, diblock copolymer can have many different forms depending on comonomer composition. In this work, we are interested from the case of diblock copolymer in thin film geometry. We want to know how the structure, morphology, and dynamics will be changed as a function of monomer-bit interaction. Here is the overview of our simulation method for diblock copolymer. First, the RIS model of a single chain of polyethylene was used to describe two intra-chain interactions. To simulate the bulk system, we introduced the Lennard-Jones non-bonding interaction. The cosigent polymer chains were mapped onto two NND lattice with grouping two carbon backbone 2 and B. For comonomer, we use different interaction parameters for non-bonding terms, using Lennard-Jones potential, which vary epsilon as 100, 300, and 350. Next, we create the thin film from the bulk structure by increasing the periodic box size in one dimension so that its melee image cannot interact. We then use multi-color simulation with multiple polycriteria to move polymer for equilibrium and trajectory data analysis. Result and discussion. Density profile, we observe phase separation in diblock copolymer thin film. As the interaction becomes stronger, the thin film density increases, strong phase separation, and sharper surface. For energetic, the inter-chain energy drops where the inter-chain interaction is increased. At the surface region, it may be expanded. Chain conformation can adopt more tight state which has lower interchain RIS energy. The interchain energy becomes higher due to better molecular packing, or the comonomer bit can come close to the repulsive portion of Lennard-Jones potential that is less 5 angstrom. For chain property, the molecular size in terms of radial alteration, both Z, Y, and Z components become smaller as the chain approach the surface from the bulk side. When the interaction increases, the chain dimension becomes smaller. For molecular orientation, we follow the anisotropic arrangement of the largest and smallest principle, both exist random or in the bulk region. Where there is a strong tendency of the large principal axis to orient parallel to the surface and the smallest axis normal to surface. The stronger bit interaction, the higher anisotropic chain arrangement. For dynamic property, we investigate the rotational and translational motion of molecular and monomer level. The decay rate of end-to-end decorrelation function and mean square displacement of the center of mass diffusion are both lower from stronger bit attraction. To compare the dynamic at the monomer level, we use the mean square displacement of monomer bit. For homopolymer chain, the curve is symmetric. For the diblock copolymer, we observe the asymmetric curve with increasing bit attraction. The bit mobility becomes lower and the curve becomes more asymmetric. This is my conclusion. I thank the PhD scholarship and HUT from the research support.